things and other things. More things. What am I doing? I was going to share the screen. Try to do share the screen. Start video. Back. Come back. Ooh. Let's see. Like question 5 on 6.3. Yeah.
You also do one division one.
Yeah, it's definitely on my agenda for sure. I didn't seem so bad, but we'll have to go over it. Okay. So we'll talk a little more about partial fractions, and then we're going to try and get into some improper integrals as well. So let's look at a few examples. I got a couple things. C's. So let's look at problems basically like 5 and 6 and 7, 8, and 9. So let's say we had something like, sure, let's do something like this. Well, this could be a little bit higher, I feel like. And that's right, it could be just a little higher. So let's do something like this. The integral of 2x squared plus 4x plus 6 over x cubed minus 16x. I'm going to do a quick check to see if I can do a u sub. U equal the bottom. It's not looking like the derivative is going to be the top. So I'm pretty sure u sub is not the way to go here. So let's see. I can factor the bottom. The degree on top is less than the degree on the bottom. That's right. I'm going to check those three things. Degree on top is less than the degree on the bottom. And the bottom factors. So if those two things are true, then we can typically, although we don't always have to, but we can use partial fractions. So we're going to write this as 2x squared plus 4x plus 6. We're going to factor the bottom as x times. We'd be left with x squared minus 16, but I should really say we need to factor the bottom completely, meaning as much as possible. So the x squared minus 16 that we would have is going to factor as an x minus 4 times an x plus 4. So then we're going to do the partial fraction decomposition, and there's going to be 1, 2, 3 pieces because there's 1, 2, 3 factors. I should really, that's not quite the right thing to say, but here, since all the factors are to a power of 1, is the right thing to say. So we're going to write this as a over x plus b over x minus 4 plus c over x plus 1. And what I should point out is it doesn't matter which order you do this in, as long as you are consistent with what you've written. So once you find a, b, and c, make sure that a is the thing that's above x, and b is the thing above x minus 4, and c is the thing above x, or however you've lettered them. Right? If you've done it differently, just make sure that you've got the right letters in the right places at the end of the day. So then this is the step that I feel like that gets forgotten after people do this too many times. The next step is just multiply both sides of this equation by this common denominator, x times x minus 4 times x plus 4. So we're going to multiply that to each of these pieces. The left side is just going to be the numerator every time. 2x squared plus 4x plus 6. The right side, you're going to cancel stuff, right? We don't want any denominators. The whole point of multiplying by this common denominator is that your new equation should have 0. That's the wrong thing. There should not be any denominators. So I'm going to get a times the x's would cancel. I'm left with x minus 4 times x plus 4. B, the x minus 4s would cancel. So I'm going to have b times x plus 4. And c times the x plus 4s would cancel. So I'm going to c times x minus 4. And then if we're doing things the most efficient way possible, we're going to use the convenient values of x. So there are 3 convenient values of x: 0, 4, and negative 4. I'm getting those either by literally actually looking at what makes these denominators 0, which I know is something we don't usually do, but that's how I'm finding them, or by thinking about what's going to make stuff 0 over here. That's an x plus 4, by the way. So I'm going to pick x equal to 4 to make that 0, x equal to negative 4 to make that 0, or x equal to 0 to make that 0. I'm just picking the things that make a lot of things equal to 0. So I pick x equal to 0. I then plug it in for every x. So I'm going to get 0 plus 6 equal to a times negative 4 times 4. Plus 0, which I'm not going to write, but we know it's there. So we're going to get a equal to 6 divided by negative 16, which we should reduce as negative 3/8. Same deal for the other two. I'm going to plug in x equal to 4. And let's see, on the left-hand side, I'm going to get 2 times 4 squared plus 4 times 4 plus 6 equal to a times 0 plus b times 4 times 8 plus c times 0. So simplifying, let's see, I've got 32 plus 16 is 48 plus 6 is 54. I'm going to divide by 32 to get b, and I should reduce that. Let's see, that's 27 over 16. The numbers don't matter. I mean, they matter, but like they don't matter that much. And then finally plugging in x equal to negative 4. On the left-hand side, I'm still going to get 2 times 16. And that's going to be minus 16 plus 6. And on the right-hand side, 0, 0, and then c times negative 4 times negative 8. So here I've got 32 minus 16 is 16 plus 6 is 22 divided by 32 is equal to c. So c is 11 over 16. And now we go back and rewrite the integral as our new integral of the partial fraction decomposition. So we're just going to rewrite the whole thing as the integral of a, which is negative 3/8 over x, plus b, which is 27/16 over x minus 4, plus c, which is 11/16 over x plus 4. Right? X plus 4? Yeah. See, these are all nice x to the first powers. They're all going to end up having integrals that are natural logs. So when I look at this, although I don't want to spend the time or the paper to write it out, what I'm really thinking of when I look at this is negative 3/8 times 1 over x. Or really the integral of that, I should say. Negative 3/8 is just a constant, it's gonna hang out. So I'm gonna get a negative 3/8 times, what's the integral of 1 over x? Say one more time? Right, except we need one more little tiny thing. Right, natural log of the absolute value of x. Same deal here. This is really 27/12 times 1 over x minus 4, and its integral is going to be, I could have read 27/16. I don't know how that 6 turned into a 2 there, except my writing's terrible. That's how it happens. So I get 27/16 times the integral of 1 over x minus 4 is the natural log of the absolute value of x minus 4. Plus 11/16 times the integral of 1 over x plus 4 is the natural log of the absolute value of x plus 4. Plus c. So that's the general process. Typically, this is the way you want to do it. Specifically meaning you want to pick nice values of x that make most of the terms go to 0. So you can solve for one of those constants at a time. Questions about this one? Okay, let's look at one that's similar to problem 6 because I want to point something out. So, yeah. Try to keep things in order here as I usually try to. Let's say we want to do the integral of x. Let's make it 6x over x squared minus 10x plus 25. So, again, I think about u sub for a second. If I let u equal the denominator, my du is 2x minus 10, and that doesn't really work out for me. I don't have a minus 10, so it's kind of a bummer. Or I don't have a minus something times 30, I guess, would be what I would need. So I'm thinking, well, does that bottom factor? Yeah, it factors. I can write this as 6x over x minus 5 times x minus 5. So here's what I want to point out. If your denominator factors, but it's only kind of like one thing to a power, you can do partial fractions. Totally works. Let me show you. So partial fractions, we can totally do 6x over x minus 5 squared. Now remember, since it's something to a higher power, we have to have every lesser power as well. So we're going to say that's equal to a over x minus 5 squared plus b over x minus 5 to the first. I'm not going to write the first. I'll point out the answer to this decomposition is not that a is equal to 6x, right? The a and the b have to be constants. So we're going to solve for a and b that make this work. Same step as always. Multiply everything by the denominator. So I'm going to get, let's see, 6x is equal to a plus b times x minus 5. And although you could pick convenient values here, this one we could just look at, and everyone should be able to, if you think about it for just a minute, you should be able to figure out what b is, just looking at it. All right, I'll tell you what I got. I got b equal to 6. Because the 6x over here has to equal 6 times x over there. There is no other option for b. Or you could do the work where you say, I can also pick a convenient value. I'm going to let x equal 5. Let x equal 5, I get 6 times 5 is 30 equals a plus b times 0. Well, that helps me find a. And then if you wanted to pick some other value for x, you could use that to find b, which would be 6, but b has to be 6. So great, then we're going to rewrite this integral as the integral of a over x minus 5 squared plus b over x minus 5. The b over x minus 5 is going to integrate just like the previous problem we did. You're going to get 6 natural log of x minus 5. But this x minus 5, this 30 over x minus 5 squared is not going to be a natural log. I should say its integral is not going to be a natural log. We need to rethink of that, I think, as the integral of 30 times x minus 5 to the negative second plus 6 over x minus 5. This part here, this 30 times x minus 5 to the negative second, just gets the power rule. So that's going to be 30 times x minus 5 to the negative first, or negative 1. Yeah, we could do a u substitution, but it's such an easy u substitution, u equals x minus 5, that we kind of just were like, well, it's almost close enough to being just x because you're just adding or subtracting a 5, that we can kind of just cheat it out and use power rule. And then this is going to be 6 natural log of the absolute value of x minus 5. And if you wanted to, we could simplify this as negative 30 over x minus 5 plus 6 natural log of x minus 5. Let's see. That is a perfectly fine way of doing it, but I will point out that you have options. Maybe you don't want options, but you've got them. When your denominator is just one term like this that factors to a power, like x minus 5 squared or x plus 4 cubed, something like that, you can totally do a u sub with a back sub. So we could also have done u equal to x minus 5. My du is equal to dx, and solving for x here, u plus 5 is equal to x. So that my integral of 6x over x minus 5 squared dx becomes the integral of, well, the bottom's going to be u squared. The numerator is going to be 6 times u plus 5 du. And most people would consider this to be an easier way to do it. That doesn't mean it's necessarily true. It just means that that's what most people think is true. All right, what are you doing here? Sorry, one sec. Okay, good. So doing it this way, we have the integral of 6u over u squared plus 5 over u squared, or simplifying a little bit, 6 over u plus 5u to the negative 2. And the integration is still essentially the same. You get 6 natural log of the absolute value of u plus 5u to the minus 1 over minus 1, which ends up being, sorry, one second. 6 natural log of the absolute value of x minus 5 minus 5 over u, which is x minus 5. Now I feel like I've made a mistake. Oh yeah, I did make a mistake somewhere. You guys see it? So here's the check. I see my answers look different, like two different, right? The 6 natural log of x minus 5 is good, but here I had a minus 30 over x minus 5, and here I have a minus 5 over x minus 5. So I should go back and check, and oh yeah, I totally missed distributing this 6 to each of those terms. That should have been a 6u plus a 30 over u squared. This should be a 30 u to the minus second. This should be a 30 u to the minus first. That would be a 30 over. So they do turn out the same. Yeah.
I'm confused about something in regards to the previous way you did it.
Sure.
So the second line there, when it says partial fractions and then to the right, why is it the denominator under a x minus 5 squared? Why is it not just x minus 5?
So here's the deal. Whenever you do partial fraction decomposition and you factor your denominator, once you've identified all the factors, you need each factor raised to its highest power and then every lesser power. Now, here's why. If you had a over x minus 5 plus b over x minus 5, there's no way of finding constants a and b so that a over x minus 5 plus b over x minus 5 ends up being 6x over x minus 5 squared. It won't work out right. And the thing is, you basically need this highest power to show up. Otherwise, the decomposition isn't going to end up being successful. It's really just because of how the algebra works. But it's harder to explain other than to say, like, if we don't have it, it's not going to work. We can look at it for a second. If you had this, if you had 6x over x minus 5 squared equal to a over x minus 5 plus b over x minus 5. Well, first of all, these already have a common denominator, so I can totally add them together. So I'm really just saying 6x over x minus 5 squared equals a plus b over x minus 5. And that's not going to end up working out, because what you're going to get is you're going to get some constant, and you have to multiply the top and bottom by x minus 5. And whatever that constant is, if it's 6, you're going to get 6x minus 30, which is not the same as 6x. So it's not going to coming out to be the right number. Just to point out, just so everyone's super duper clear about this, I want everyone to see it is definitely true that 30 over x minus 5 squared plus 6 over x minus 5, that is equal to the thing we started with, 6x over x minus 5 squared. Right, if I actually do this, if I get a common denominator and say, okay, well, this is 30 over x minus 5 squared plus 6 times x minus 5 over x minus 5 times x minus 5. Well, look what I've got. I've got 30 over x minus 5 squared plus, let's see, 6x minus 30 over x minus 5 squared. And when I put those together, I exactly get what I started out with. So that's why we're doing what we're doing, because we are starting with this and working backwards to get to this, because we are able to integrate that relatively easily.
If the quadratic happened to factor, so that each factor was different, like if it was x minus 5 and x plus 5, would you still need to do that, or then could you just
Then you would not need to do that. So again, so just to be super clear about the partial fraction decomposition, so we'll make up something ugly for a second. So if you're trying to integrate something like, I don't know, 2x cubed plus 5x plus 1 over x. Let me make this interesting. Well, not interesting, but sure, let's just do it like this. Let's say it's x cubed times x squared minus 25 times x plus 7 to the 4th. Well, first of all, I didn't factor it fully. I should really write this as 2x cubed plus 5x plus 1 over x cubed times x minus 5 times x plus 5 times x plus 7 to the 4th. So what we have, sorry, the x is up here. So we have a bunch of linear factors, x plus 7, x plus 5, x minus 5, and x. So those are our linear factors, meaning you just have x to the first. I know x is to the third, but I'm thinking of it as like, you can think of this as x minus 0 if you wanted to. It's x minus 0 to the third. The linear factor is the x, and then we're raising it to the third power. X minus 5, x plus 5, and x plus 7. And then some of them are repeated linear factors because you have x to the third. So this is a repeated 3 times linear factor. And so is x plus 7. It's a repeated linear factor. When you have repeated linear factors, you need the highest power of them and every lesser power down to 1. So if I was doing this partial fraction decomposition, I would write 2x cubed plus 5x plus 1 over all this garbage, x cubed times x minus 5 times x plus 5 times x plus 7 to the 4th. And typically, if I'm writing up decomposition, I just start from left to right. Although, again, doesn't really matter what order you decide to do it, as long as you are consistent after you started this. So I'm going to write this as, I'm going to give myself lots of room, a over x cubed, and then every lesser power of x to the whatever. So I'm going to have b over x to the second, c over x, because I have x repeated 3 times, and then every lesser power. And then for x minus 5, I just have d over x minus 5. Same for e over x plus 5. But then for x plus 7 to the 4th, I'm going to have 4 different things: a 4th power, a 3rd power, a 2nd power, and a 1st power, which again is awful. So f over x plus 7 to the 4th plus g over x plus 7 to the 3rd plus h over x plus 7 squared plus I over x plus 7. This would be completely terrible. No one's ever going to ask you to do this, but they could ask you to set up the partial fraction decomposition for something this heinous. Again, this is not a lot of work to do other than writing it out if they're just asking you to set it up. No one's asking you to integrate this ever. It's way too complicated. I'm sure the numbers are really, really terrible. Okay. Questions about this? All right. So again, repeated linear factors, you just have that highest power and every lesser power down to 1. And the reason why is because we need them. If you don't have them all, you won't, the partial fraction decomposition, you won't be able to actually make this fraction equal this other thing, because you'll be missing like an x somewhere that you need. Let's look at a couple more. Let's look at some examples with polynomial division. So let's actually start off with a really, really seemingly easy one. Well, not seemingly, it is easy. So it would be really easy to just start doing partial fractions here, and we would be wrong. Let me show you why. So here's the wrong thing to do. Don't do this. Don't even write this down. If we just start doing this, x squared minus 4 over x squared minus 1. I should have factored that. X squared minus 4 over x minus 1 times x plus 1. If we try to write this as a over x minus 1 plus b over x plus 1, I'm just going to point out to you that if I actually got a common denominator on the right hand side, so I'm going to write this as a times x plus 1 over x minus 1 times x plus 1 plus b times x minus 1 over x minus 1 times x plus 1. If I actually simplify this a little bit, I've got ax plus a plus bx minus b over x squared minus 1. Is there any way you can find an a and a b so that this is equal to x squared minus 4 over x squared minus 1? And the answer is absolutely not. A and b are constants, right? Like 5 or 7 or negative 2/3. And there's no way that a times x, when a is a constant, is going to equal x squared. This is a problem. We can't deal with it until we have dealt with first doing the polynomial division. So if your degree on top is greater than or equal to the degree on the bottom, it's almost always the first thing you do is just polynomial division. So this is going to mean do some polynomial division. So we take our numerator and we divide it by our denominator. In this case, it's very easy. What do you multiply by x squared to get x squared? 1. So 1 times x squared minus 1. We subtract x squared minus x squared is 0. Negative 4 minus negative 1 is negative 4 plus 1, which is negative 3. And then we have to actually rewrite the integral. So we're going to rewrite the integral x squared minus 4 over x squared minus 1 as the quotient, which is 1, plus the remainder divided by the divisor. And now the integral of 1 is just x. And for the integral of negative 3 over x squared minus 1, that's where we're going to have to do partial fractions. So, yeah. So then we would say, and here's where, yeah, I would probably do it the following way personally. If it's just one constant term on top like this, I would probably rewrite this as the integral of 1 is x. And then I would write this as minus 3 times the integral of 1 over, let's factor that, x minus 1 times x plus 1. And now we do partial fractions. So then we're like, okay, 1 over x minus 1 times x plus 1 equals a over x minus 1 plus b over x plus 1. We multiply both sides by the denominator to get 1 on the left equal to a times x plus 1 plus b times x minus 1. Then we pick convenient values of x. If x is equal to 1, we get 1 equals a times 2. So a is equal to 1/2. And if x equals negative 1, we're going to get 1 on the left. If there's nowhere to plug in x on the left, so we just get the constant term over there, equal to a times 0 plus b times negative 2. So b is going to equal negative 1/2. And then that's what we're going to write over here. So we're going to get x minus 3 times the integral of 1/2 over x minus 1 minus 1/2 over x plus 1. And then we integrate. So we get x minus 3 times 1/2 natural log of the absolute value of x minus 1 minus 1/2 natural log of the absolute value of x plus 1 plus c. And that's how we deal with improper fractions. That's actually, so when you have a fraction, like just like with regular fractions, like 5/3 is an improper fraction because the numerator is bigger than or equal to the denominator. When you have improper polynomial rational functions here, where the degree on top is bigger than or equal to the degree on the bottom, we have to start with division before we can do anything else really. Let's look at a couple more examples because this is a pretty straightforward example. It's relatively easy. Let's look at 2 more examples. Relatively easy. It's still not easy. It's just easier than what we're going to do. So let's look at this next one. Let's see, what did I come up with here? Okay, yeah, that's the one. Yeah. So look at the integral of x to the 4th plus 3x squared plus 6x plus 2 over x cubed plus 2x squared plus x. So one thing I have come to notice over the years is usually, but not always, but usually if the numbers look pretty heinous or big in your rational function, it usually means someone has done the work so that the answer comes out to be not super terrible. Like often it'll mean all your constants end up being nice integer values instead of heinous fractions. So something usually to look forward to. But first and foremost, I see a degree on top that's bigger than my degree on the most. So regardless of anything else, right? I don't even know if this bottom factors, although it does factor. But regardless of anything else, I have to start with the polynomial division. There's nothing else I can do. There's definitely not a u substitution I can do here. So, okay, let's see. X cubed plus 2x squared plus x into x to the fourth. I should fill in the missing term, so I'm going to put a 0x cubed plus 3x squared plus 6x plus 2. It's good to fill in the missing powers of x just so that things line up right when you do the multiplication. So I'm going to multiply x cubed by x to get x to the fourth. So x times all of this is going to be x to the fourth plus 2x cubed plus x squared. And then we subtract. Or you can do the things where you change the signs. I've never been a fan of that personally, but you can do that thing if you like to. I'm subtracting those always. The first term should always subtract to 0. That's why we picked what we picked here to get what we got there. 0x cubed minus 2x cubed is minus 2x cubed. And 3x squared minus x squared is 2x squared. Bring down the next term, repeat the process. Multiply x cubed by negative 2 to get negative 2x cubed. Negative 2 times x cubed is negative 2x cubed. Negative 2 times 2x squared is minus 4x squared. Negative 2 times x is negative 2x. Subtract. That minus that is 0. 2x squared minus 4x squared is 6x squared. And 6x minus 2x is 6x plus 2x, which is 8x. And we're done with the division, right? This power here, this degree here is less than that degree here, so we can't continue on. So now we have to rewrite the integral. So we're going to rewrite this as the integral of the quotient x minus 2 plus the remainder 6x squared plus 8x plus 2 divided by the divisor x cubed plus 2x squared plus x. And here's where someone's going to try and slip one past you. At this point here, you would normally be thinking we should do what? Right, totally. Partial fractions is where I would go to. But sometimes they'll try to make it so, well, you could do partial fractions here. Partial fractions would totally work 100%. However, now is the time to check for a u sub for that piece over there. So if I rewrite this as the integral of, if I do the integration of this part just to kind of get it out of the way, x squared over 2 minus 2x. If I'm left with this integral here, 6x squared plus 8x plus 2 over x cubed plus 2x squared plus x. If we check letting u equal the denominator, our du is 3x squared plus 4x plus 1 dx. And that, if I multiply that by 2, it looks exactly like that. So this is a good time to see that we should use the u substitution because it's much, much faster than doing the partial fractions. So sometimes that'll happen. Sometimes someone will try and sneak one of those in there. Watch out for it. It's not terrible if you miss it. Well, I mean, it's terrible in that you're going to spend a lot more time doing the problem if you miss it. So do look for that u substitution. So I would say du divided by 3x squared plus 4x plus 1 equals dx. And then I might rewrite this. Sorry, there should be a plus sign there. I might rewrite this as x squared over 2 minus 2x plus the integral of, I might factor out the 2 from the top here just to make it super obvious what's going to happen. So this is 2 times 3x squared plus 4x plus 1 over x cubed plus 2x squared plus x times my du over 3x squared plus 4x plus 1. That cancels that. That becomes u. So I end up with x squared over 2 minus 2x plus the integral of 2 over u du, which is x squared over 2 minus 2x plus 2 natural log of the absolute value of u plus c. And then finally plugging back in what our u is, I get 2 natural log of the absolute value of x cubed plus 2x squared plus x. Fun times. It's kind of cool. Yeah.
Which is, I'm pretty sure that our professor has been demoing the long division step in a different way. Where,
Oh.
she like, and I don't fully understand what she's doing.
Okay.
She makes the numerator look identical to the denominator, and then to the right side of that, she does addition or subtraction.
Oh, yeah,
So that
sure.
it will actually make that true.
That doesn't always work. It is, I know what you're saying. So let me point out, sure. So. Yeah, that's. It wouldn't really work that well here. Because so here's what I think you're saying. Just to clarify. I think you're saying something like if we had, I'm going to make a very basic example just to make it clear. If we had something like the integral of, I don't know, 2x plus 5 over x. Now it's a terrible example, James, fine. Sorry, trying to come up with something that's, sure, let's do that. Let's say we had something, this feels super contrived. Let's say we had 3x squared minus 13, sure, over x squared minus 4 dx. So if you had something like that, you could say, well, the top kind of looks like it's 3 times the bottom. So you could write this as the integral of 3 times x squared minus 4, but that's really equal to 3x squared minus 12. But I need to be minus 13, so I could tack on a minus 1 there and then do that. Is that what she's doing?
I think that's what.
Okay, yeah. That's perfectly fine. It just doesn't, it only kind of works in some corner cases. Like it's not super applicable all the time. But you could totally write this as the integral of 3 times x squared minus 4 over x squared minus 4 minus 1 over x squared minus 4. And then, yeah, this part's going to become just the integral of 3. Okay. But back to the one we did before. I mean, no, it's not easy enough to see how to do it that way that it's worth the time to think about. Like you need to I would encourage you to do it the long way. So I kind of see what you mean though, like looking at homework problem 8, for example. So here's homework problem 8, or at least my version of it. 3x squared plus 26x plus 53 over x squared plus 7x plus 12. I can see that I have 3 times that being that. So I'm probably thinking of this as 3 times x squared plus 7x plus 12. And then let's see, 3 times 7 is 21x. There's still another 5x I need. And 3 times 12 is 36. There's still another 17 I need. So you could do it like that. But I think it only really works nicely when the top and the bottom have the same degree. So I'm not going to finish this one, but I'll point out this is going to equal the integral of 3 plus 5x plus 17 over that factors as x plus 4 times x plus 3. You could get away with doing it that way, but it's just as simple to do the polynomial long division, right? So if I did this one the long way, I would be doing x squared plus 7x plus 12 into 3x squared plus 26x plus 53. And when I do that, x squared times 3 gives me 3x squared. And I multiply 3x squared, 3 times 7 is 21, 3 times 12 is 36. And then we subtract, and we get 0, 26 minus 21 is 5x, 53 minus 36 is 17. And look, we get the exact same leftover part. So I think you're better off doing it this way, but this, I guess, works. I would point out, though, that it is in problem 9, for example, my version of problem 9, which we're not going to do, is heinous. It's 4x to the 4th plus 27x cubed plus 59x squared plus 55x plus 27 all over x cubed plus 6x squared plus 9x. I know there's like a 4x because 4x to the 4th divided by x cubed is 4x, but I don't know what the constant term is going to be without having to really like put some effort in the thing. At that point, you should just be doing the polynomial long division. So that's what I would say for that one.
And that's what I'd say in general. You're almost, unless it's very, very obvious, like, I feel like this isn't even that obvious, but this is fairly obvious. You really should do it the more general long way. Like in this next example. I don't know if we're gonna get to the other stuff I said we were gonna get to today, which is too bad because we need to talk about it. When you guys have a test on Friday? Yeah, okay. All right, so let's look at this example I came up with, and then we'll try to talk about the other thing briefly. Where's my example? There it is, right there. The integral of 2x to the 5th minus x to the 4th minus 4x cubed minus 5x squared plus 20, all divided by x to the 4th minus 4x squared. Definitely looks like the bottom factors, like a lot. But before we can even think about that, we have to deal with the polynomial long division because the degree on top is certainly greater than or equal to the degree on the bottom. So let's do the long division. So in my, I forget what this thing's called. There's a name for that. I don't remember what it is. So I've got my 2x to the 5th minus x to the 4th minus 4x cubed minus 5x squared plus 0x plus 20. I got to fill in that missing term there. And then here, you might want to write this as, I don't really want to write the 0x cubed there. You could, I'm not gonna. I'm gonna write this minus 4x squared. I'm gonna be careful. So let's see, x to the 4th times 2x is gonna get me 2x to the 5th. So 2x times x to the 4th is 2x to the 5th. And 2x times 4x squared, or times negative 4x squared, is gonna be a negative 8x cubed. So I have to put underneath that. So it's gonna be a minus 8x cubed. Subtract. That minus that is 0. That minus nothing is just negative x to the 4th. And negative 4x cubed minus negative 8x cubed is negative 4x cubed plus 8x cubed, which is plus 4x cubed. Bring down the next term. Repeat the process. What I multiply by x to the 4th to get negative x to the 4th? Negative 1. So negative 1 times that is negative x to the 4th. And negative 1 times negative 4x squared is plus 4x squared. Subtract. That minus that is 0. 4x cubed minus nothing is 4x cubed. Negative 5x squared minus 4x squared is negative 9x squared. And bring down the 20. I could bring down the 0x as well, but I guess I didn't need the 0x there, but it's good to have it just in case you need it. Okay, so here's what we've got. We've got the R integral is equal to the integral of the quotient 2x minus 1 plus the god-awful looking remainder 4x cubed minus 9x squared plus 20, all divided by my divisor, which I will factor. It's x squared times x squared minus 4, which I guess I could factor further and should factor further. Okay, so now it's time for the partial fraction decomposition. I should point out, we're gonna end up getting the integral of 2x minus 1 plus some other stuff, right? Like an a over x, a b over x squared, a c over x minus 2, a d over x plus 2. So let's do the partial fraction decomposition. 4x cubed to the 4x cubed minus 9x squared plus 20, all divided by x squared times x minus 2 times x plus 2. Equal to, doesn't matter which way you do it. I'm gonna do a over x squared plus b over x plus c over x minus 2 plus d over x plus 2. And then we multiply both sides by this common denominator. So we end up getting this numerator on the left, 4x cubed minus 9x squared plus 20 equal to, when I multiply by this, I'm going to cancel the x squared. So I'm going to get a times x minus 2 times x plus 2. And multiply by the b over x. One of the x's will cancel. So I'll get b times x minus 2 times x plus 2. I'll get c times x squared times x plus 2. And I'll get d times x squared times x minus 2. And now we continue our journey of picking convenient values. What are my convenient values? What's one of them? Yell it out. -2. Awesome. What's another one? Someone else. Wait, what's another one? Someone else. Great. And that's all of them. We don't have enough convenient values to find all of our A, B, C, and D, but that's okay. It'll work out still. So for x equals -2, I plug it in. I get 4 times -8 minus 9 times 4 plus 20 equal to 0, 0, 0 d times 4 times -4. So let's see. Okay, -32 minus 36 is -68. Plus 20 is -48. So you get -48 equals -16 times d, and divide both sides by -16 to get 3 is equal to d. Awesome. Okay, so then for x equals 2, same deal. 4 times 2 cubed is 32, minus 9 times 4 is 36, plus 20 equals a times 0 plus b times 0 plus d times 0 plus c times 4 times 4. Let's see, 32 minus 36 is -4 plus 20 is 16. 16 equals 16c, so c equals 1. Now I plug in x equal to 0. Let's say I get 0, 0, I get 20 on the left. I get a times -2 times 2. And all the other things are 0, 0, 0, 0. So I'm getting a equal to 20 divided by -4, which is -5. Okay, I'm left with needing to find b. So here's what I would typically do. I would equate some coefficients. Specifically, I would pick the highest power of x that I see on either side, which if I multiply out the right-hand side, or if I look at the left-hand side, is going to be x cubed. So I'm going to equate the coefficients of x cubed, assuming that b is going to come up in that. If you can see that the thing you're looking for is not going to come up in that, pick something else. But if we look at x cubed, on the left-hand side, I have 4. On the right-hand side, I have to be careful. Do I have an a times x cubed? I sure don't. So I multiply this out. This is a times x squared minus 4. I don't have an a times x cubed. I definitely have a b times x cubed, because if I multiply this out, I get b times x times x times x. So I've got a b times x cubed. I would also have a c times x cubed, and I would also have a d times x cubed. But I know what c and d are. So I have that 4 is equal to b plus 1 plus 3. Which means b is equal to what? I think b is going to be 0. That happens sometimes. Sometimes one of your, or more than one of your constants is 0, which means you don't even use that term. So when I write out my partial fraction decomposition, it's going to be -5 over x squared. Plus, I'm not going to write 0 over x. I'm just not going to write that term. It's not there. And then c was 1 over x minus 2. And d was 3 over x plus 2. And then we integrate. Integral of 2x is x squared. Integral of -1 is -x. This I'm thinking of as -5x to the minus 2 and just using the reverse power rule on it and getting -5x to the -1 over -1, which really I should simplify as plus 5 over x. And then I'm going to get plus the natural log of the opposite value of x minus 2 plus 3 times the natural log of the opposite value of x plus 2 plus c. Fun times. Yeah. So polynomial division is the thing. I do think you are better off doing it the long way, unless it's super duper extra obvious that it just comes out very nicely. Yeah, what time is it? 2:55. Okay. So let's briefly get into talking about the other thing, improper integrals, just to give you an idea of what's coming your way. And I think you've already talked about it in class a bit, but just kind of give you some small intuition into it. I'm sure you've seen these two examples. The integral of 1 over x and the integral of 1 over x squared is x from 1 to infinity. But I want to say a couple things about them. So first off, if you're looking at this integral here, integral from 1 to infinity of 1 over x dx. This is the wrong, so don't write this down or make it very clear that what I'm about to do is the wrong thing. So this is wrong. Integral of 1 over x is the natural log of the opposite value of x from 1 to infinity. And that's equal to the natural log of infinity minus the natural log of 1 The natural log of infinity goes to infinity, natural log of 1 is 0, to infinity. And the reason this is not right, although you still end up with the right answer, so this is the wrong process. And it's wrong because we can't just treat infinity like a number. Like a number that we just plug in whenever we want. Sometimes people do it anyway. Some teachers definitely do it that way, although they really shouldn't. But the idea here is really when you're doing improper integrals, where you have an infinity in one of your limits of integration, or the other kind where your function is undefined somewhere at one of your endpoints or somewhere in between your endpoints, you have to use a limit. So the very first thing is, once we've identified wherever in your limits of integration you have a problem, infinity is always a problem, it's not a real number, we're going to replace that problem with a letter of your choice. B is typical for the upper limit, A is typical for the lower limit. Some people like to use T for everything, some people like to use Z for everything. Is your teacher doing something specific? T, okay. So I'm going to rewrite this integral from 1 to infinity of 1 over x dx as the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. I'm just replacing the problem with t and then saying t goes towards whatever the problem is. And then we just kind of ignore this limit the whole time until we've done everything else we can possibly do. So I'm still going to write the limit because I should. But then I'm just going to do the integral like I normally would. We know how to integrate 1 over x. It's the natural log of the absolute value of x. We get the natural log of the absolute value of x evaluated from 1 to t. And then we're going to still ignore the limit, but write it. And then we're just going to plug in our limits of integration. Sometimes you'll see people drop the absolute values here because t is positive and 1 is positive, so we don't need the absolute value of them. People often write this as just the natural log of t minus the natural log of 1. You might take an additional step and say, oh, the natural log of 1 is equal to 0, and rewrite this as the limit as t goes to infinity of the natural log of t. But then we have to actually look at them and be like, oh, okay, well, what does the natural log function do as the inputs get further and further and further to the right? And the natural log gets higher and higher and higher and higher and higher. Very slowly. It's not a very fast increasing function, but it does get bigger and bigger and bigger without bound, meaning its limit is infinity. So what do we say about this integral? Well, we say two things. Thing one, this integral from 1 to infinity of 1 over x dx diverges. And then sometimes you might be asked additionally, which direction it diverges in, meaning does the area under that curve go to positive infinity, go to negative infinity, or is it some sort of weird oscillating thing where you can't tell? In this case, we would say this integral from 1 to infinity of 1 over x dx diverges to infinity. Or positive infinity, I should say specifically. Oftentimes in web work, if it diverges, they will ask you, does it diverge to infinity or negative infinity, or is it one of those cases where you can't tell and it doesn't exist? Technically, diverging to infinity means the integral also doesn't exist, but we're just being more specific about how we are saying it doesn't exist. So I'll point out this is interesting, I think. It's kind of weird to think, and I'm just going to show you this picture instead of drawing it for you because we're out of time. But what we'll see next time as well, or you may have already seen, right? The function 1 over x in red here, this area underneath it is infinite. Whereas this seemingly not that much smaller function, and we haven't talked about yet, but 1 over x squared, the area under that curve from 1 to infinity is finite. That area is just equal to 1. So it's interesting that like this small sliver of area here between 1 over x squared is actually infinite in value because it's so much bigger, but it seems like they don't look that different. So that's very quickly an example of what we're doing with, I actually get the name for it, improper integrals. We'll talk more about them on Wednesday. And yeah. I hate that this class is after your class for some of you. It's not ideal, but it's what we've got. I'll try to find some resources for those of you that have the midterm before class. So you only them. For those of you, classes will not be, attendance is optional on Friday. Everyone will get marked present. Still fill out the attendance form. I know I haven't updated attendance in a while. I apologize. It's just got other things I got to do. I'll get it updated. It'll be fine. But yeah, for those of you who have the exam, you'll have the exam. For those of you who have a class on Friday, come if you want to come. Obviously, if you have the test later in the day, we'll reviewing for the test. But if you've already had the test, you're welcome to come, but you probably don't need to come. Okay, that's all I got. And I'll be over and dropping. Stop the recording.